and I'm going to let that run. In the meantime, I'm going to jump over to my results and see what happened in my first demo. So here's something that's important. When you start the demo, it will take a screenshot of whatever's on your screen. So try to make it like an axon view, because this is actually quite useful, especially if you're making major geometry changes. I like to see these thumbnails updated. The next thing is that this gives you a bunch of information about the results. So it tells you the weather station, it gives you your floor area, your exterior wall area, your lighting, power, and people. Again, this is part of those settings. For example, if it's set as an exercise center, it will have a setting, how many people per square feet. So if your building's 3,600 square feet, there will be 40 people. If you increase the size of your building, it will change the number of people. It also gives you the exterior window ratio. So when we start doing custom windows, it will calculate this for you, which is a valuable number to know, because basically the more windows you have, the worse performance of the building. And it knows like roughly how much fuel and electricity costs for that area. Next thing it gives you is this, and this is extremely important. This is the energy use intensity. So this is how much energy is used per square foot per year. So what's good about this is, let's say Juan does his building and he gets this value of 104 kBTU per square foot per year. Okay, and Jose does his and he gets 50 kBTU per square foot per year. Basically, you're comparing apples to apples because you're comparing it per square foot. So if, let's say his building is twice as big and his building is small, half the size, it doesn't matter. It is factored in the square foot. Okay? And it also does it per year. So basically, this is the most important value out of everything on this screen, is this number, total EUI. What you want to do as you run these tests is you want to get that number as close to 0 as possible. It's not going to reach 0. But yes?
If it's underground,
Mm-hmm.
and the sun isn't hitting it, how do you show that?
So if it's underground, you just move the building below level 1. Okay? And I'm, I've actually played around with it, and it does reduce the load, but not as much as I thought it should. So if you're doing that, just maybe you can email me and let me know, because I can take a look and see if the numbers are about right. But what you do is you just move it below the level 1 ground level. The other thing Scott Davis was mentioning is that if it's sloped, for example, and so it's like ground on one side and not ground on the other side, you can create a separate mass and not enable the energy model for that, and that should work as as that thermal mass. Again, I think that's something that's a little bit more complicated, and so if you're doing that, then just come talk to me and I'll help you. Okay, okay, so anyways, so this is it. This is the main thing. Look at the total EUI, okay? And find out, compare your project to other people's projects or other designs. The other thing you want to look at is electricity versus fuel. So you notice we're using more electricity here than fuel, and that represents, potentially that you have more cooling needs, because air conditioning usually uses electricity, heating usually uses fuel. Okay, now this is also a very important thing. Okay, there's also life cycle, so you can multiply everything times the, the square footage and times the years. 30-year lifespan for a building is typical. If you can increase that, of course, you're also being more sustainable, because every time, every 30 years you have to tear down a building, it's not very sustainable. But this is important for you guys, the renewable energy potential. I want to remind you that your project is in the middle of the desert, and so you don't have like power lines, right, and massive stores of energy available to you. So basically having a carbon neutral building, or something that produces enough energy for itself, is something you should all be striving for. That is a major goal of the studio. So here it's saying that, again, let's look at these numbers. With a high efficiency roof mounted PV system, and it knows how big your roof is because you have modeled that, you can produce this number of kilowatt hours per year. Okay, so is that enough electricity? Well, I don't know, because these numbers are all, none of them are given in the correct units to compare this. So let's do just a quick calculation. I know my life cycle electricity use is shown here. Okay, 2,600,000 kilowatt hours. Okay, so let's just take that number, 2,658,357, and let's divide that by what to get an annual an annual energy use. What number should I divide this by? 30, right. Great. So I'm using about 88,000 kilowatt hours per year. Okay? And my PV system here can generate about half of that. Okay? So you can see if I could reduce my energy needs so that they were, below the 40,000, then I could almost provide enough electricity for my building. Does that make sense? So you could either try to make your roof bigger, or you could try to reduce the energy, which we'll work on. Of course, we will make that better because we're at 80% window wall area right now, which is too high. Okay, a few more things. And it will also calculate the carbon emissions. And again, as we know, in the end, what matters is carbon emissions. That's what affects climate change. Okay, and then there's a number of graphs. I'm not going to spend a lot of time going over them. I think most of them are pretty self-explanatory. This is kind of interesting. This shows you the difference between electricity and fuel. So as you can see, electricity is 81%, fuel is 19%. So again, the cooling demands are much greater. Okay, and then we notice here, when I was mentioning that there was more cooling, these are not even in the same unit, so that doesn't make sense to look at these numbers, kilowatt hours versus kBTU. It's better to look at this graph here to understanding what is the real problem in this climate. The real problem is cooling because it's hot there and because this building is being used during the day. That's why there's so much of this is electricity use. Next graph, fuel. Basically, what is your fuel being used for? It's being used for your heating system, okay, 75%, and then also for your domestic hot water. That's what your heating is being, your fuel is being used for, okay? So if you have, natural gas at home, typically those are the things that it's being used for. Electricity, what is the electricity being used for? 60% of it is being used for HVAC. A big chunk of it, 17%, is being used for lighting, and then what's the rest being used for in this light pink color, salmon? What is that? So the rest is being used for miscellaneous equipment, our refrigerators, our cell phones, our computers, etc. And actually this is quite useful. It's a little bit advanced for what we're doing, but if you really want to get into it, and you can click on any of these if you want to see them slightly bigger, this actually tells you how the heat is coming, basically the heat gain and loss through the building. So as you can see, there's things that are contributing positively and things that are contributing negatively. So what is giving me heat is miscellaneous equipment. That generates heat, okay, all year long. It's always on top of 0. Light fixtures, same thing. That's generating heat. Occupants, that's generating heat. Window solar, basically there's heat gain coming through the windows. That's also a positive in terms of heat balance. And then window conductive, as you can see, in terms of the heating load, we are actually losing heat through the windows. We are losing heat through infiltration, through underground surroundings. Okay, so if you did an underground project, ideally this number would be much higher. It's not really even showing up on mine. A little bit, because you do get some heat loss through the slab. And then interior surroundings, so through my walls and my roof and my walls, okay? So for my cooling load, what's happening here is we can see the biggest thing that's contributing. Yeah, question, Henry? So anyways, back to monthly cooling. If you can see here, the main thing that is contributing to my needing more cooling is this orange color. So basically what's happening is I have a lot of heat coming through my window in terms of solar heat gain. In the summer, that's a bad thing. So this is bad, okay? Anything above 0 is bad. Anything below 0 is good, okay? There's a bunch of other things too, but that's the main culprit. And then several other graphs. So this is my fuel consumption. Here's my electricity consumption. It's higher in the summer, more air conditioning. Fuel is higher in the winter, more heating then. And then these are some familiar graphs that you guys are familiar with, and some climate studies. This one's kind of nice. I mean, these are all self-explanatory. You can look at them yourselves. But this one is the diurnal temperature, so it really gives you an understanding of how the temperature changes from the coldest part of the day to the warmest part of the day. Okay, let's go back. Let's look at our window 60 window wall area. We now have 2 results, okay? And actually, before I do that, I'm going to run another one. I'm going to click on this again. I'm going to go to energy settings. Again, you don't have to click on it. It's just a habit of mine, but you don't have to click on it. Change it to 40% and hit OK. And then I'm going to hit Analyze Mass Model again. And this time I'm going to name this number 3, and I'm going to name it 40 window wall area. And run that. So while I'm running that, I'm going to look at the 2 that I do have completed. So I can look at both of them together by highlighting both of them with my control button and hit compare. And my screen is not really big enough, okay? So, but you can probably do this a little bit better on your screen. Actually, maybe I'll pull this down. So let's look at the 60 window wall area. The main thing I want to go to is the total EUI. That's really the first sign of whether or not it's better or worse. So in this case, when I switched it from 80% to 60%, you can see that the energy use dropped to 96 from 104. So it is an improvement, and you can calculate what the improvement was, like 10, 15% or whatever. And then you can look at the comparison graphs to see what the difference is. So for example, you can see, and you have to be careful, sometimes the legends are not the same. So like this one goes from 60 to -20, and this one goes to -20 to 70, so it's slightly different. But the point is that you're reducing these the Windows Solar component. Okay, and let's take a look at our life cycle electricity use is 2.4 million now. So let's see if our PV system is coming close to supplying enough energy for at least to cover the electricity. So 2472000 divided by 30, it's 82,000, still really high. So we're still not quite there. We're at 47,000. So that's still not enough. And this also gives you the wind potential, as you can see, is not very high. So I would not suggest using that in this area. Let's take a look at our newest one. It's still processing. While that one's processing, let's go and make another change.